In this brief lecture, I want to discuss with you a little bit of measurement theory in the statistical sense. Just for the record, this is not measurement theory in other senses which might be more common in pure math. So what we're discussing here today is basically the problem that we've gone over before in this lecture series on the measurement of variables specifically. I want to briefly start by way of explaining what measurement theory is about by reminding you of the difference between a variable and an observation of it. Although we often refer to variables in the data set, this is strictly speaking not a very correct usage. You should keep in mind that these data that you see, so a column of information, for instance, recording the education levels of, say, 10 people who are listed in 10 sequential rows of a data matrix, those are realizations of random variables. They're not the variable itself, which is just the abstract notion of a property that varies across individuals. So what this means is that we never actually directly observe a variable. Indeed, it's not really an observable thing. It's not even, in some sense, unobservable in the same way that a true population mean in some sense could be observed, but it simply isn't in practice. A variable itself is more like a concept that the term observe just doesn't really make sense for. So what we actually do observe are separate pieces of information about instances of this variable. So there's a difference between any such property, like the level of education someone has, or a person has, to put it more generally, and specific observations of it. So what we are really interested in is kind of this concept, but we need information about it to analyze it. So there are a few different intermediate links between these two things, and one important link is that between the concept itself and the instrument that measures it, whether this is a literal instrument such as a bathroom scale measuring how many kilograms someone weighs, or a survey instrument that asks people, I meant to finish the sentence, something like their age or their education. So we're often concerned with the general phenomenon of measurement error, which we've already discussed before in this class, which is the problem of linking the concept to the observations of it. Sometimes this is pretty straightforward and there's not much measurement error. So for example, someone's money income is a well-defined concept. If we could assume away the problem of obtaining honest answers from respondents, so for instance, people often hide their income because they're worried about being investigated by the IRS or because of social desirability response bias, meaning that some people might think their income is too high or too low. But assuming those things away, so assuming this problem of kind of like user error, if you like, or respondent error, the actual way to record observations is pretty simple. Assuming you have a way to deal with inflation, which is pretty easy to do, all you have to do is just ask someone their income. Less sociologically, another simple example would be correctly measuring someone's height. So you can just take a tape measure or kind of a wall measure like you see in the doctor's office, and for most purposes, it's going to correctly capture the notion of height. But other times we have this task of trying to measure some construct that we believe to be latent, which means that it's not directly observable. And again, distinguish a couple things here. We said before that properties in general aren't, strictly speaking, observable. You can just observe its realization. Here, this is kind of a separate issue. When we say that a construct is latent, we mean that there's no direct way to observe it in a particular individual. So not only is the property, like in principle, unobservable, just because that's what, this kind of most abstract notion of a property, it's not a thing that has like a discrete instantiation. It's something that we can observe in people, but it's bigger than any one person. But here we have this other problem, which is that we might know it when we see it in a particular individual, but we can't really say how we define it, right? So for instance, a good example of a very latent variable might be someone's style or whether someone is cool or not, right? these are things that you might know socially. It might be well known and fairly objective whether or not someone is part of the in group or the popular crowd, but it might be very hard for anyone to describe what it is that makes someone part of that or not. So think also about this kind of other example here. You might take someone's fitness. So a little more specifically, most of us would say that fitness exists in some sense, but there are many reasons that we might distrust someone's self-report of this quality. So we've got social desirability response bias, but here, unlike in the income example, where if we could just get people to honestly answer the income question, it's not totally clear that we could get someone to accurately answer any sort of fitness question. For example, maybe you care a lot about cardiac fitness. Maybe you care a lot about strength. You might care about fitness as it pertains to some specific sort of act of fitness, like being able to run a mile or a 5K, but you might mean it in the sense of, okay, this person can do a whole variety of activities in, relatively good time controls and that sort of thing. So that's one sort of fundamental problem here, is that it might not be clear how we can directly capture this thing. Sometimes we might not even be sure whether that property exists. So for instance, the classic kind of Myers-Briggs classification of people as introverts or extroverts, it's not completely clear whether or not that's a coherent sort of grouping of people in the first place. As you can see, this can all get very complicated. I'm mentioning some of these issues just to give a bit of a preview of where we're going to go in a little bit. At a high degree of psychometric sophistication, we can use these complicated techniques. Some of them are, for instance, structural equation models, which is used in factor analysis, as a way of determining whether observed data are consistent with certain of these hypothesized latent constructs, but that all gets pretty complicated. There are some simpler methods that I want to teach you in this class that still in some ways get at the problem of measurement, and I described just one here, which is scale construction. Scale construction, in brief, is a technique that we can use to get basically around at least the one problem that I mentioned before, which is that sometimes it's hard to devise a single question that seems to truly capture a concept, and it might be the case that a battery of related questions is necessary. You can think about this as being, in principle, similar to, say, a test of your ability to read. Any single question probably isn't going to be a very good measure for a variety of reasons. Some of them we'll get more specific about, but the general principle that you ought to ask someone 10 or 20 related, hopefully closely related questions, but also ones which aren't identical, is probably a better approach. So this kind of test is what we basically mean by a scale. So scale construction is this simple approach. It draws again on the simple algebra of variances, although I'm not going to describe the mathematical detail. It's in the appendix here. You can just know that fortunately the math here, although it's quite beautiful, is also fairly simple, and it's also pretty easy to describe non-mathematically. So a scale basically ends up just being the sum of certain items that we believe to represent an underlying property. For example, as we'll see in a little bit, we might believe that someone's overall attitude towards abortion can be captured by their score on a battery of questions about abortion on the GSS, the General Social Survey. It's a pretty straightforward belief, and it turns out that this straightforward approach is totally adequate. We just need some tools for assessing whether or not the resulting scale that we have does what we hope that it does. And in particular, we generally ask two questions about scales. Is the scale reliable, and is it valid? And these two terms are fairly generic, even though they're used to mean very specific things, and it may be more helpful to think about these as meaning internally trustworthy and externally trustworthy, respectively. So reliability is a little bit harder to describe, actually, even though it's more fundamental, and so let's start with validity. So validity, or external trustworthiness, is a little bit harder to measure, but the concept is simple. It's how close our scale comes to describing reality. If a scale is not totally valid, then there is some known persistent gap between the readings of the instrument and the underlying property. So you can think about this as like a bathroom scale, which generally consistently overestimates the weight of someone who steps on it. More sociologically, you could think about a set of questions about police reform written by an advocacy group, whether for or against police reform. Those questions will generally induce people, unless the group is trying very hard to be neutral, to systematically under or overstate their interest in reform. So this is easy to describe, but it's harder to catch because we, generally speaking, can't observe the true underlying construct in most cases. That's what it means for a variable to be latent. It's not directly observed. And so this would be true even if we had data on all members of our population. So measurement error is actually separate from sampling error. It could exist, and it sometimes in principle does exist, even when we have data on all members of the population, not just a sample. There are some cases where you could try to externally match your scale to some objective property. So for instance, if you have a scale of political attitudes and you think about voting for a Democrat or a Republican as a kind of external test, that's one way around the problem. But note that this only works when we sort of define the true scale as voting patterns in a given election, but maybe this isn't what we mean by left or right-wing voter. So this is, generally speaking, a problem in scale construction that's worth thinking about, but is impossible to fully resolve in most cases. An interesting question that we actually need before we even talk about validity is that of reliability. Reliability is simpler and more fundamental. It's a question of whether or not a measurement even captures something coherent. And a classic way of measuring this is to think about variance in a scale or a composite variable. Remember that the variance of any variable is given by this here. It's effectively the mean squared deviation of a variable. You can decompose that variance into the variability that is shared between the component variables making it up when you do have a composite variable, and variability that's unique to each variable. The proportion of variance which is shared is one way of taking a reliability coefficient, and the one that we'll discuss here, the one that corresponds to this very simple notion, the proportion of shared variance, is known as Cronbach's alpha, after Cronbach, a pioneering American statistician. A conventional, although it also is arbitrary, much like 95% confidence is arbitrary, although widely used and not ridiculous, but simply there's no reason to pick that particular value other than convenience. So a conventional, though arbitrary, cutoff for a reliable measure is an alpha of 0.8. Here, since we're not going to focus too much on the mathematical details, I'm just going to give an example from the 2018 JSS as promised before. The details on the math are given in the appendix. I do want to mention a few caveats quickly though. So first, although scales are sometimes understood as a means of turning qualitative variables into quantitative ones, this isn't strictly correct. Scales require that the underlying variables have meaningful means and standard deviations. This is true for the special case of binary qualitative variables, so questions that ask for a yes-no response. So do you support abortion in this case or not? Do you support abortion in that case or not? But this isn't strictly true for ordinal variables, so things like Likert items. Happily, nominal variables can be turned into sets of binary variables easily, even if the resulting variables have meanings that are very specific, if nothing else. So for example, you might turn a Likert item that says, how satisfied are you with your current doctor? And you get responses such as somewhat, very, not satisfied, very unsatisfied, blah, blah, blah. You can turn that into a set of questions that asks, are you somewhat dissatisfied with your doctor or not? Are you mostly dissatisfied with your doctor or not? And so on. And those variables are going to have a very particular interpretation, but in principle, you can turn any set of ordinal variables into more sets of binary variables. So that's one thing to mention. Second, you should generally speaking try to standardize the items involved, that they're not already on a comparable scale, to make sure that no variable overpowers the others, unless this is part of your theoretical lens, where you think that one variable is more important. Third, it's a good idea to ensure that correlations between variables are positive. If negative correlations are observed, you can just reverse score one of the variables. This, by the way, all of this practical advice isn't strictly speaking necessary for SOC257 in the summer 2023 version because I will make your scales for you. I just want you to understand a little bit of what's going on underneath the surface. So let's come to our example and then we'll wrap up this short lecture. Below I'm showing you the correlation matrix for a set of variables about abortion in the General Social Survey. And these variables, ab any, ab defect, ab ins pay, ab poor, ab single, represent questions asking the respondent for a binary outcome opinion on whether or not a woman should be able to get an abortion for any reason at all, ab any, if the child has a strong sense of a defect, ab defect, if she'll use insurance to pay for it, ab ins pay, 4 if she's poor, ab poor, and 5 if she is unmarried, ab single. This class unfortunately doesn't have adequate time to cover correlations, but you can interpret the correlations in this matrix quite easily. Just a couple of facts to know here. Basically, correlations are standardized covariances, and for the Pearson correlation coefficient in the sample, which is denoted with R, and this is true in the population as well, where it's denoted rho, R is between -1 and 1 inclusive. That's actually because it's a funny kind of a cosine, in fact. But anyways, you can interpret basically R's that have larger absolute values, so whether they're close to -1 or close to 1, as being indicative, of a strong linear relationship between two quantitative variables, and this works if the variables are binary. So in this case, for instance, we can see a relatively good correlation between ab defect and ab any, a very strong one between ab poor and ab any, and a very strong one between ab any and ab single. And we can find some other strong correlations. So for instance, the correlation between ab poor and ab single is 0.83, which is very high for a sociological variable. So in this case, you can see that the items in this matrix generally have a close relationship, meaning that a lot of their variance is shared, and consequently the alpha, the proportion of a composite variable consisting of someone's score on these 5 items, generally the variance of that composite variable, which we can generically just call Z, or maybe we should call it simply something like A for clarity, that composite variable A has a variance which is largely due to shared variance between these 5 variables. What this tells us is that the variable captures something that all 4 questions about abortion that should read 5 have in common. It's a reliable measure of something, although we can't really be sure just what, because all we know is that we have a internally valid or sort of hanging together measure. But you can make reasonable guesses, of course, about what this might represent. My dumb joke here, this probably isn't a scale measuring someone's interest in yo-yo competitions. It probably has something to do with abortion. Big surprise. And specifically their opinions about the legality of abortion in different scenarios. But what exactly it's capturing is somewhat hard to say. Perhaps you would argue because of the inclusion of this ab any variable. By the way, these ones on the main diagonal here, I probably should have explained this, are there because these are the correlations between an item and itself, right? So, of course, those things have to be perfectly correlated. And the reason that the top half of the matrix isn't filled in is that the correlation matrix is symmetric. So the correlation between ab any and ab defect must also be the same as that between ab defect and ab any. So some software will print like 0.4894 up here, 0.5004 up here, but most software doesn't bother to do that. Stata, for instance, where I pulled this from is one of them. Okay, so anyways, we see these strong correlations between these items. So you could argue that maybe because of the inclusion of this overall ab any variable, that what this really captures is something like someone's overall opinion towards abortion, and these other questions are just sort of subsidiary. But it appears that there's something more going on here, and it might be somewhat hard to say exactly what, but we could name it something like tolerance towards abortion, perhaps. The score on the scale is going to be somewhat abstract. It's best to interpret it relatively or in a bivariate analysis, so thinking about the difference in means between two groups, for instance. It doesn't matter so much what the score is for each group, so much as the difference between the two groups, but you can also standardize these scores as well. The resulting variable, in any case, is quantitative and can be used in any analysis which uses quantitative variables. So I wanted to wrap up by simply showing a histogram of this resulting composite variable. You can see here 1 means that someone was more favorable towards abortion, and we see a fairly healthy spread of opinion here. But what we have is a quantitative variable in the classic sense that is fit for analysis in any kind of quantitative research strategy, such as if you're taking the difference in means between two groups. That's where I'll wrap up this lecture because I'll help you construct your scale since it's a little bit hard to do in sheets, and I'll give you back a vector of data. But I wanted to explain a little bit to you where that variable comes from, and I'll also provide the alpha, and I'll ask you to interpret that as well. Thanks for watching. Have a great day.